Hi there, my name is Christopher Wirst and welcome to the second video for Homework 1, looking at part 2 of Homework 1 that says, assuming that the decrease in air temperature with altitude can be modeled entirely by the adiabatic reversible expansion of pockets of air in ideal gas, starting from the basic equation of fluid statics, derive expressions for the 1, air pressure, and 2, air temperature as a function of altitude. Now behind me I've got my whiteboard. So I'm going to start with a picture to represent the first situation, the air pressure, and then start deriving some of these out. Alright, so now that I've got my marker, I'm going to start over on the left here. So we have some, we'll call it a pocket of ideal gas, air, and it's changing in height. This will be H. And down here at 0 it is some pressure, we'll call it pressure 1. So P equals P1. And up here at height Z, we'll say P is equal to P2. Some arbitrary second pressure. So let's start with the basic equation of fluid statics, which is the change in pressure with related to the change of height, dP over dz, is equal to negative rho, the density of the gas or fluid, because air works like a fluid, multiplied by g, it's not a good g, the acceleration due to gravity. Now, we also know that it's an ideal gas, so we're going to use our old friend PV equals nRT, pressure times volume equals number of moles, ideal gas constant times temperature. For part 1, we're going to be looking specifically at pressure. For part 2, we're going to be looking at temperature. We also want an equation for density. Density is equal to mass over volume. We know that. It's also equal to N, number of moles, times capital M, which is molecular weight. So now with this, with all of these lined up, we can start going for translating this to get specific pressure. So to start, we're going to combine these two equations, and I'll draw this down here because we will need this entire equation sheet. So rho is equal to, or density is equal to mass over volume is equal to number of moles N times molecular weight goes to density is equal to and we're also going to use V over here. So V is equal to nRT divided by pressure, and since this is on the bottom, it flips. So we'll have pressure times M, or pressure divided by M over nRT, and this just realized mass, not density, mass is equal to number of moles times molecular weight. That makes more sense. If you were looking at this going, something doesn't quite look right, it was that. Now that we have that, we can substitute in, goes to density equals pressure, number of moles, molecular weight divided by number of moles are ideal gas constant temperature over moles cancels out, equals pressure times molecular weight divided by ideal gas constant times temperature. I am going to mark these p's as p prime, simply because it's a dummy variable. We're not looking at specifics just yet. So with that, we can now substitute in here with the basic equation of fluid statics. dP over dz is equal to, again, change of pressure over height, negative pressure, molecular weight over ideal gas constant times temperature times G. And with this, we can, little differential equation, where it's separable, so we can separate it and go to derivative of pressure dP over P is equal to mg over, or negative mg over RT dz. And from here, we'll make two wiggles as we may do integration. Wiggle 1, dP over P is equal to negative molecular weight, the acceleration due to gravity, the ideal gas constant, and temperature are all kept constant, so they don't need to be in the integration. That's an awful integral. And dz. So now, what do we need? We need limits of integration. This is going from pressure equals P1 to some arbitrary pressure P2. I'm going to note it as P. So P1 to pressure. And then this integral is going from height 0 to z. And then this z is, again, a dummy variable. So 0 to z. This goes to the integral or the antiderivative of 1 over, call it x, is natural log of x. So goes natural log of pressure from P1 to P is equal to negative, that's negative molecular weight over ideal gas constant temperature times z from 0 to z prime. And we're going to translate this down here. So ln of, because this is ln of pressure P minus ln of P1, that's a quotient, so it's natural log of P over P1 equals negative molecular weight, a constant acceleration due to gravity, RT. This is z minus 0, so it's just z. This is kind of sideways. So I'll start evening them out. I'm also going to have to crouch, but that's okay. And now from this, if we take e to both sides, e and the natural log cancels out, it's e to everything, so it goes to power stance. Pressure over P1 is equal to e to the power negative molecular weight times constant acceleration due to gravity times z, the height, divided by ideal gas constant times temperature. Finally, that goes to pressure is equal to P1, the initial pressure, times e to the power of negative mgz divided by RT. And we have our first equation. So now I'm going to translate this up here, and then I'm going to erase everything besides that picture, because we no longer need any of this, because I need all the room I can get for this next bit. So let's transpose this up here. P is equal to P1 e to the power of negative mgz over RT. I can erase all of this. Now, here, I'm going to note or t is equal to T2, because either T is constant or pressure is constant, or T equals T1. Okay. Those are the two cases. I'm just using the same illustration for them both. So I'm now going to use the first law of thermodynamics that says the change in internal energy du is equal to heat added plus pressure multiplied by change in volume. Now, the heat added is 0 because it's adiabatic. That has been stated in the problem. So this is 0. We also know that du is equal to amount of heat added CV times delta or dt, change in temperature, is equal to, I'm going to now use this, the ideal gas law up here, because we don't want pressure in this equation. We want to get it out. So I'm going to make this an arrow so it's easier to understand. Goes to, and we know that P is equal to nRT over V. We're going to assume that N is 1, the number of moles of air is 1. So that just goes to RT over V dV. Real quick, this should be negative. It's better. And this, if we do some changing, we can get, goes to CV, amount of heat added, multiplied by change in temperature, divided by temperature. Again, this temperature is a dummy variable, is equal to negative R, ideal gas constant, change in volume divided by volume. So, this means that from here we can do some integration, so I'll add a wiggle and a wiggle. This temperature here is going from T1 to some T, and this V1, this volume is going to some V1, from some V1 to some unknown volume. Again, I'll put primes here to make it a dummy variable. So now we can do the same thing, goes to, again, like earlier, both of these are going to be natural logs, so this is CV, specific heat added, natural log of, and again, because this is T prime from T1 to T, I'm going to have to write this underneath, is equal to negative ideal gas constant, natural log of V prime from V1 to V. So from the starting volume to some arbitrary volume where we stop. I'm going to take this over here, I'm going to transpose it over, and put it so that, and have it go specific heat added, natural log of temperature, or T divided by T1 is equal to negative R, that's curving again, natural log of V divided by V1. Now, doesn't look like we can do much here. However, we can say that, quick aside, we know from thermodynamics that CV, specific heat, is equal to R times Cp, which is the specific heat capacity, RCP. This also means that specific heat capacity is equal to specific heat added, Cv, divided by R. That'll be coming up in a minute. This can go to Cv over R, we'll call it negative, natural log of T over T1 is equal to natural log V over V1, which means this will go to specific heat capacity when we take the E's of these, this cancels, it goes to T over T1 e to the power of Cp, with, again, Cp being specific heat capacity, is equal to volume over starting volume. Now, if we do a quick cross multiplication or move over, we can have T is equal to, the temperature is equal to volume times T1 over starting volume e to the power of, or, e to the power of Cp. Actually, no. This is fine. This is not. Well, this is fine. This is fine. This equation is incorrect. It's actually Cp, constant, the heat capacity is equal to R plus Cv. That's better. Or Cv, plus R. Good. Then this here is incorrect because this E will cancel out, but these will still be raised to the power. We'll have this temperature times temperature divided by starting temperatures to the power of negative Cv over R. Better. Now this, we've seen the BAM, and we're also going to get rid of this. We've seen this, but now we want to go back to the pressure because we want to get all of this into this here equation, into the workup that we did here. So, because we know V is equal to this, V is equal to nRT over P, we know that goes to T over T1 is equal to V is on top, so nRT over P, nRT over, we'll call this P, -1. And then V1 is equal to nRT1, P1, -1. And in R shown are the constants, so they stay the same. And then the P's flip, so that goes to, and this is 2, by the way, negative specific heat added over R goes to T over T1 is equal to the power of negative Cv over R is equal to, it's equal to T1 over T over T1 times P1 over P. So now we can move this over to this side, flip it, and we can take it as T T over T1 to the power of negative CV minus 1, which we can just call CV plus 1. CV plus 1, CV over R plus 1. Specific heat added over ideal gas constant plus 1 is equal to starting pressure over actual pressure. Now we can take this, and because R, we can divide all this by R, and have it CV plus R, all divided by R. And because we know that CV plus R is equal to CP, the heat added plus the ideal gas constant is equal to specific heat capacity. I'm going to erase this, make this specific heat capacity over R. Now, we can flip this to make to get over here, i.e. take the root of Cp over R, it's going to flip it, it goes to temperature is equal to starting temperature temperature divided by starting temperature is equal to starting pressure divided by pressure, C with R over specific heat capacity. Simply move this starting temperature over T temperature equals T1 starting temperature times starting pressure time divided by pressure to the power of ideal gas constant over Cp over here specific heat capacity. We finally have our equation written, but we know that P is equal to P1 to the power of E negative mg Z divided by RT. So that means that this will go, and we can sum it in here. T is equal to T1 to the power of P1 over P1, and because E is to the power of negative molecular weight times acceleration due to gravity times height divided by ideal gas constant divided by temperature, we can take that and we can flip it, make it positive, and put it in the numerator. So I'm just going to E mgz over RT to the power of R divided by Cp. These cancel. Actually, we're going to take this. We have our temperature equation here, which I'm still not sure is correct. I understand where I made a mistake. I made a mistake here. Small, but it is important. Right here, I divided this by R. When I did all of this, that's all okay for now. But when I made this negative CV and said that this, because it's going over, and you flip it, and it's negative CV minus 1, and you can make that CV plus 1 effectively, or CV plus R through the thing, you can make that C on the constant heat capacity. That's incorrect. What I needed to do was make this positive by flipping this natural log. So if I go back, erase here, make this V1, make this V1, this will be positive, this will be positive, this will be positive, and then T1 is on top, P1 is on top, T and P are on bottom, this is positive again, and then these two flip. And then when this flips over, it's plus 1, and then you can get a heat capacity. This will flip, this will flip. This division is still correct, but this will flip. Yes, we wanted pressure on top. Now it's correct, and I realize where exactly that happened. So we're going to take this, take this, there we go. And I'm going to erase some of my work and write it just below the pressure to make it T is equal to starting temperature pressure over starting pressure, power of R over constant heat capacity, or specific heat capacity. Then erase my work because we're almost done, but I need more room and I don't have it. And we're going to go back to here. And we're going to go back to M over V, back to change in pressure over change in height is equal to M over V, negative mass over volume times gravity. Again, just taking this and moving it over, that's an S. Z is equal to negative N molar weight. V, we're going to make V is equal to nRT over P, so P is up here. nRT, cross out the N's, and then we can put P in, T in, and from here we can substitute temperature in. So T is equal to T1 goes to change in pressure over change in height. Again, no, that's correct. Change in height is equal to negative molecular weight over pressure divided by R times starting temperature, and this will be pressure to the power of Cp over R. No. Yes. No. Negative Cp over R. Negative R over Cp multiplied by, because pressure is on the bottom, it flips up, starting pressure times positive R to the specific heat constant. Now we're going to move this over and have it be positive. And we're going to move the change in height over. I also want to make a specific note that, because we found this earlier, T over T1 is equal to P over P1, and you can flip that, but saying that the relationship between the two is equivalent. So that'll be useful for later. So we have, goes to change in pressure, or pressure times R to the power of ideal gas constant divided by specific heat capacity. Change in pressure is equal to dz. So this is all constant. So negative molecular weight pressure over. And I do want to note that this would be, because these pressures combine, I can erase that. This would be +1, and because we flip it, it's now -1. Pressure is gone over R, starting temperature times starting pressure to the power of R over Cp. Now we're going to integrate, so integral dz from starting height z1, and not a z, z1 to z2, and then pressure from P to, from P1 to P. So this integral cancels out this 1. So it goes to the pressure to the power of R over Cp. And the coefficients of that are 1 over this, or this, so that's Cp, specific heat capacity, over ideal gas constant is equal to from specifically P1 to P is equal to negative molecular weight divided by ideal gas constant times starting temperature is equal to starting pressure, R over Cp. I'm just copying this over, then times Z from Z1 to Z2. I'm going to have to crouch one more time, but we should be able to fit everything. So, this means that Cp over R times pressure R over Cp minus P1 R over Cp is equal to negative M over RT P1 R over Cp Z2 minus Z1, and then we can copy this over. These two R's are going to cancel, and we'll have pressure to the power of R over Cp, and if we move this over as well, we'll have Cp is equal to pressure, starting pressure, R over Cp, 1, because this 1 is this from a moved over, and then this starting pressure to this power factored out, minus molecular weight done over starting temperature, specific heat capacity is Z2 minus Z1. Then the last step we're going to have goes to pressure is equal to Cp over R, P1 1 minus M over T1 Cp, Z2 minus Z1, to the power of the inverse of this, Cp over R. So we have this equation, we have the pressure, we have the change in height, and we know, because these two are roughly are equivalent, that T is now equal, I'll write it down below it, goes to T is equal to starting temperature 1 minus molecular weight, starting temperature, specific heat capacity, finishing height minus starting height, i.e. the change in height, the all raised to the power of specific heat capacity over ideal gas constant. And with that long derivation over, we're finished. Thank you very much for watching. And I hope you have a wonderful day.